That's basically a very simple demonstration of a typical drive-by download process. So what happened was DIG had a persistent cross-site scripting vulnerability. The attacker used that to inject the iframe, and in the backend, Metasploit or Drivesploit was used to serve the JavaScript exploit. Okay, the motivation behind building this. Antivirus provides solutions that monitors websites and detect malicious contents 24/7. We use multiple behavior, heuristic, and signature-based technologies. Most technologies are developed on our own, but we also integrate Antivirus because behavior-based technologies that we use are very, very costly. And when you have to scan millions and millions of URLs a day, you end up paying hosting companies a whole bunch of money. So we started a while back looking if we can find some antivirus solutions that can be coupled with our behavior analysis. But they're very, very expensive. And so we spent a lot of time testing our own technologies and also selecting antivirus technologies. And the key is the key to this type of testing is how good are we and them at detecting new drive-by downloads instead of old ones. But how do you get new drive-by downloads that don't exist? That's the problem. So we ended up getting the old exploits and then mutating them by hand to generate new exploits, and then testing out all these antivirus technologies in our own. And we ended up writing big messes of code. It was very hard to debug, and it was just taking us a lot of time. So we needed a good framework to help us replicate, manipulate, and mutate exploits found in the wild. Note we didn't say obfuscate. There's a difference, because when we say mutate, we're changing the raw basic JavaScript exploit in its raw form, and not in its obfuscated form, into new derivatives. So Drivesploit is born on top of Metasploit. Initial findings. Antivirus capabilities differ greatly. Desktop and API versions differ greatly in performance, meaning that an antivirus technology which really performs well for its desktop version may perform very poorly for its API version, which is the version that we want to use, right? It's basically a library or a console or an API for us to call. And also cost does not equal to performance. Surprisingly, the most expensive ones may not be the ones with the best performance, at least according to our testing. And so antivirus versus drive-by downloads. So we ended up getting quite confused, and we started calling these antivirus companies, and we were like, the results don't make sense, blah, blah, blah. And they're like, well, what are you testing? Well, we're testing JavaScript. And then they don't want to answer the call. And we call again, and we're testing JavaScript. Well, can you give us some explanation? Well, JavaScript is sissy stuff, We don't. So JavaScript to them is not hardcore stuff. Maybe it's true, right? I mean, yeah, PEs and everything and assembly, these are very hard. But unfortunately, we have to deal with JavaScript when we deal with drive-by download. And so, according to their explanation, as you can see, in our drive-by download process, the URL generator is JavaScript, the exploits are JavaScript, the malware itself is the PE binary, and they'll say, and this is what they said, well, we'll detect this part. So during the drive-by download detection process, if in the end that's going to exist and we're going to detect that. But unfortunately, that's not the case. Why? Because usually a malicious domain serving that piece of malware is going to be taken down 2-3 days later, but the injected domain, such as dig.com, the injection is still going to be there for a long time. And although that piece of malware is not valid anymore, is not active anymore, we still want to be able to detect that. The other thing is, nowadays, a lot of DNS, a lot of ISPs, when they find out that domain is malicious and serving malware, would block that domain, even though that domain is still active. And then sometimes it's just the, in the economy, the subscription period is over. You bought us, you paid us to serve for 2 days. It's now past the period. You haven't paid up, so we're temporarily shutting it down. That doesn't mean that we're not going to reopen again. And so we want to focus on all of the JavaScript. And that's why we can't just rely on PE detection. So the deal here is ECMA-SCRIPT, which is JavaScript, VB-script, Adobe.js, and ActionScript. And so we want to take this part out. Okay, we want to take this part out and replace the exploit server with Metasploit and use Meterpreter or something similar as payload, which basically does memory injection instead of trying to download a piece of malware and writing it to disk and have that malware do the malicious stuff. We want a payload such as Meterpreter, which also exists in the wild. And so that we can test this out, and we can test out the abilities of technologies just detecting the injected JavaScript or the JavaScript exploits. So drive-by downloads, what do they want to do? They want to avoid detection at the victim's desktop. They also want to avoid detection by UTM's gateways. And they also want to avoid detection by automated monitors, which are services like those that we provide, or live for as long, and they basically want to live for as long as possible. So, conclusion. What are we going to do? First, reduce exposure. And you do that by selectively. Serve selectively. For example, you can serve only to each IP only once. You log the IP that you've served to. Because if the visitor visits you for the first time and your exploit doesn't succeed, forget about it, right? But don't serve to him the second time because he might be somebody working at an antivirus company. Avoid detection and analysis. Then you got to mutate well. So Drivesploit basically is trying to mimic these two goals of drive-by downloads. Serve selectively. So at the HTTP level, this is what we implemented into Drivesploit. Serve only to fresh IPs. Serve only to particular referrers. This happened to the Gumbler mass SQL injection that happened in Japan. And few security vendors were able to detect this on the spot when it exploded, because Gumbler was very selective about the referrer. It only served to referrers from Google. And in our case, in our example, for example, since we've infected DISEC.com, we can also specify, well, we are going to only serve to referrers coming from DISEC.com. Makes sense, right? If you're connecting to us directly, sorry, you're not somebody that we want to infect. We want to keep our 0-day for a bit longer. Particular agent strings, so that we only serve, if this exploit is for IE7 only, we want to serve to IE7 only. If you connect with the Firefox, we want to serve to you. If you're a Google crawler, if you're a Yahoo crawler, we don't want to serve to you. Blacklist. Blacklist of security vendor, well-known crawler IPs and security vendor IPs. We don't want to serve to those. And that basically covers the first part, which is serve selectively. The second part, script mutation. This part is for both the exploit and also for the payload. The goal here is not to obfuscate. A lot of JavaScript exploits has been using existing JavaScript packers, but that's very easily picked up by Antivirus. So the new ones all don't. The goal is not to obfuscate, but it is to mutate the raw form and bypass signatures. So we want to try not to have fixed components when we generate the JavaScript code or the new mutated JavaScript code. And we want to try to use common operations. So we don't want to use rare operations that nobody used, because then Antivirus can say, well, this operation, only 0.01% of JavaScript use those, and they're mostly exploits. We don't want to have those. So this is basically what makes up of a JavaScript exploit. There's a shellcode. There's the memory correction part, heap spray, and trigger. This is how a piece of shellcode looks like. Basically just very long list of strings, which converts to bytes. This is the memory corruption part. Oh, we're using IE peers as our example here. Memory corruption part, and we're using the exploit that's provided by Metasploit for IE peers vulnerability. And this is the heap spraying part. And finally, this is the trigger. This is the actual trigger that would execute the piece of malicious JavaScript. And then usually this whole part is sometimes, especially in the old days, obfuscated into a big blob, and then deobfuscated. So there's the obfuscated form and there's the primitive form, as we've mentioned in a previous slide. And so you would start with the trigger, and the trigger would then cause the deobfuscator to deobfuscate the blob, and then execute the the heap spray and then the memory corruption. So with this entire part, the primitive or raw form, we want to mutate, and then for the triggering part, we want to prevent in case we are inside a sandboxed or detection environment. So we want to know if we're inside a sandboxed environment, then we want to prevent ourselves from executing anything. So mutation features implemented so far. We've implemented 5 main features so far. One is JavaScript random variable auto replacement. It accepts a piece of JavaScript. It parses the JavaScript according to the JavaScript grammar. It identifies all names, including variable names and function names, and it auto replaces those variable names and function names with random names. There is already a class in Metasploit called obfuscate.js that does similar things, but you have to identify all the names yourself for it, which is very error prone in our testing process because sometimes we just miss some variables or function names. And also when we do that, it just creates a big mess. So we want to have one function call and say, this is a piece of JavaScript. Replace all the variable names and function names with random variables of our definition. We want every random variable to be of 4 to 10 characters in length. So right now it's all random. We're thinking about adding a dictionary to it so it doesn't look strange, right? If a dictionary of, 1,000 words, that may work. And passes back the new JavaScript and a vector of old new name mapping. So you know which of your variable is replaced with which name. And this is how you actually use it in Drivesploit. The second one is very, very commonly used. It's called JavaScript concat string obfuscation. So this is how you use it. Basically, you call it, and you give it a piece of string, which can be the shellcode. And this is Metasploit, as you know, has a lot of encoders already. But when you're putting shellcode inside JavaScript, you have a lot of ways to further obfuscate that piece of shellcode because you can execute JavaScript. So this is a very commonly used but very effective algorithm, and that is I give you a piece of JavaScript, a piece of shellcode, and then you split the strings, and then you generate JavaScript that add the strings back and pass me back the JavaScript. So I'll show you how this works. This, for example, is our shellcode string. We would randomly chop it according to how you want us to chop it. So, for example, chop every 4 to 8 characters. We randomly chop it into segments. We would then assign the segments to variables, okay, to layer 1 variables, and then we would scramble these assignments so that they look like this. All right, so now, as you can see, the middle section appears first. This makes it very hard for heuristic-based pattern-based detection algorithms. So that's layer 1, and then we would do layer 2, right? We will add these. We would then add these two together into layer 2 variables, and then we would then again scramble these.